Have you ever stopped to think about what's actually happening inside your phone or your laptop or, well, pretty much any gadget you own? It all feels like some kind of magic, right? But it's all built on a foundation that's actually incredibly simple and, honestly, beautiful. Today, we're going to pull back that curtain and look at the tiny, unseen brains of the operation, logic gates. They are the decision makers that power our entire digital world. So, let's just jump right in with a massive question. How in the world does your phone do, well, everything it does? You're scrolling through social media, you're sending a text, you're taking a picture. It is making countless calculations every single second. How is that even possible? Well, the secret lies in mastering a very, very simple language. And here it is, the answer. It's all thanks to this little thing called a logic gate. At its heart, a logic gate is just a teeny tiny electronic circuit. Its whole job is to look at one or maybe two incoming electrical signals and then spit out a single new signal based on a very specific rule. And those signals, they represent the simplest information possible, a 0 or a 1, off or on.
Okay, so let's get into this language of circuits. It's actually super straightforward. When a circuit has no juice, no voltage, we call that a binary 0. When it's got full power running through it, we call that a 1. That's it. And to keep track of what each of these gates does, we use a handy little cheat sheet called a truth table. It just shows you every possible input you can give a gate and the exact output you'll get back. So, now that we know the language, we can finally meet the stars of the show, the three most fundamental gates. I like to think of these as the primary colors of the digital world. With just these three, you can start to build pretty much anything you can imagine.
First up, we've got the simplest one of all, the NOT gate. You can think of this one as the opposite gate, or maybe the rebel of the group. Its entire personality is just doing the exact opposite of whatever you tell it to do. It's got one input and one output, and it keeps things very, very simple.
And check out its truth table. It's about as simple as it gets. You feed the NOT gate a 0, boom, it spits out a 1. You give it a 1, it gives you back a 0. That's its only job. Flip the signal. Simple, right? But as you're about to see, it's incredibly powerful. So yeah, that's the one simple rule you got to remember for the NOT gate. It is the absolute foundation of inversion in digital logic. Whatever state you put in, the opposite comes out.
All right, on to our next gate, the AND gate. Now this is the strict one. Think of it like a super exclusive nightclub bouncer, or maybe a high security door with two separate locks. To get through, you have to satisfy all the conditions. It has two inputs, and it is very, very picky about them.
And when you look at its truth table, you can see that strictness in action. If either input is a 0, the output is a 0. If both are 0, still 0. The only way, the one and only way you can get a 1 out of this thing is if input A and input B are both a 1.
So to put it in circuit speak, where high just means a 1, the output is high only if the first input and the second input are both high. That's the AND gate in a nutshell. And now it's time to meet the AND gate's much more chilled out sibling, the OR gate. If the AND gate is that door with two locks, the OR gate is a door with two different doorbells. Pressing either one will get the door to open. It is not nearly as picky. And its truth table totally reflects this easygoing nature. Look at that. The only way you can get a 0 out of an OR gate is if both inputs are 0. If input A is 1, or input B is 1, or heck, even if both are 1, the output is always going to be 1. It is very happy to say yes. And there's its simple rule. The output is high if A or B is high. And with that, we have our complete basic toolkit for digital logic, NOT, AND, and OR. But what happens when we start combining these basic tools, putting them together? Well, as we're about to see, we can create some brand new, really powerful gates that are basically just flipped, inverted versions of the ones we just met.
So, say hello to the NAND gate. The name literally tells you exactly what it is. It's a NOT AND. Just imagine taking the output from our strict little AND gate and immediately plugging it into that rebel inverter, the NOT gate. What comes out the other side is a NAND gate.
And its truth table proves it. Just look. It is the exact perfect opposite of the AND gate's table. Everywhere the AND gate outputted a 0, the NAND outputs a 1. And in that one special case where AND gave us a 1, NAND gives us a 0. It's a perfect flip. And, as you can probably guess, you can do the same thing with an OR gate to make something called a NOR gate.
Now, this might just seem like a neat little party trick, but these inverted gates, NAND and NOR, they have a hidden superpower.
Trust me, they are way more important than they seem at first glance.
Which leads us to a really fascinating question. We've just learned about a whole bunch of different gates. But what if you were stranded on a desert island and you could only have an infinite supply of one type of gate? Could you still build a computer?
The answer, which is kind of mind-blowing, is yes. Absolutely. Both the NAND gate and the NOR gate are known as universal gates. And what that means is that with enough of them, chained together in just the right way, you can perfectly create the function of any other logic gate. So how on earth does this work? Let's just walk through it. You can build a circuit that acts exactly like our easygoing OR gate by using only 3 NAND gates. As you can see here, first you use 2 NAND gates to just invert your original inputs, A and B. Then you feed those 2 new flipped signals into a third and final NAND gate. And what comes out the other end? It mimics the OR gate's behavior perfectly. This whole idea of universality is what makes building microchips so efficient. You really only need to perfect how to make one type of gate really, really well.
Okay, so we've been talking a lot about logic and rules and these abstract ideas. But these gates are real, physical things. So how are they actually built on a tiny piece of silicon?
Well, in the real world, these gates are built from billions of microscopic switches called transistors. A long time ago, an early type called TTL logic was the standard, but it was a real power hog. Today, pretty much everything uses a newer, way more efficient technology called CMOS. CMOS gates are incredible at saving energy. They basically only use power in the instant they're actively switching from a 0 to a 1 or back again. That efficiency is the single biggest reason our phone batteries can last all day long.
And that really brings us to the big, incredible takeaway here. The entire digital universe, from the simplest little calculator all the way up to the most advanced AI, it's all built from these few, simple, unwavering rules. It's just a beautiful example of how you can create nearly infinite complexity from a very simple set of building blocks.
So I'll just leave you with this thought to chew on. We've seen how a few simple logical rules can build our entire complex digital world. But where else do we see that same pattern? Think about something like DNA or language, or even music. What other incredibly complex systems in our lives are really just simple rules repeated over and over and over again?